here, but others are new. I think you will find this place quite intoxicating in terms of ideas and connections. So I focus my work on buildings and their performance over the life cycle and how we can improve that. So why would that be interesting relative to energy? Is it well known, or has this been shared with you in terms of the role of buildings in the context of the energy consumption of a country like the US? What percent of the total energy that the US uses is used in buildings? 30? Thanks for making an educated guess here, or at least a guess. 30%, any other bidders? 60? So it depends what you count. It's somewhere between 40 and 50%. So the operation of the building typically seems to use about 39 to 40%, at least that's the most common data I've seen. And then opinions differ a bit how much is also used in the, for the materials of buildings in terms of the embodied energy there. One calculation I did a while back that still I find a little flabbergasting, but it has been at least two people that know quite a lot about this haven't been able to find a fault in the calculation, is the energy that was used for the materials, building materials, that we throw away each year in the US. We throw away, by the way, about half a ton of building stuff a year per person in the US, which I realized even though if I'm cutting down on our home garbage, I'm still contributing half a ton, which is much more than I think we throw away in our house over the year. So we throw away about half a ton a person per year in building materials. And the energy that was used to produce that is about equivalent to the electricity of California per year, or the energy used in Switzerland for an entire year, for all the energy. So that still seems a little staggering to me, but as I said, I haven't found, a couple experts that have looked at the calcs and they didn't find a sort of order of magnitude level mistake. So buildings have a huge impact on our lives because we spend a lot of our productive and leisure time in the buildings. So as Churchill said, we shape the buildings and then they shape us. And so that's what I find really interesting dynamic. And then they, of course, have a huge impact in the environment. So one thing that, since many of you are new to Stanford, that has really happened at Stanford in the last 10 years is the many institutes and programs that have sprung up that focus on large global issues that bring together people from various departments. So that's why you see a bunch of these affiliations that I and many of my colleagues have to various centers, institutes, and programs, which is really, I think, a fantastic way of building on the strengths of the traditional academic disciplines and bring them together to address truly critical global issues. So one way to look at the energy in buildings is how do you best balance supply and demand if you were in charge of this whole area and you had to provide every minute, every second, the energy needed for these buildings. And I think that's where you also see a lot of work going on in smart grid. And buildings, because they're a major consumer of the energy, especially in the middle of the day, right? We need a lot of energy in California because we're lighting office buildings in the middle of the day, which is kind of crazy, but that's the situation. So we need to run really bad power plants to satisfy the peak demand, which comes from lighting office buildings in California. So there's definitely opportunities we have to improve that, right? And those are the plants that have the biggest negative impacts. So what, at the end of the day, we want to study from a building perspective is how do buildings really function, and where are there opportunities to reduce or shift energy demand so you can, in buildings, so that you can not impact the activities of the users, because at the end of the day, they have to make money, we have to write papers, we have to do good research here and in the buildings. So we don't impact that output, but we use the energy and we can cover the demand with the best production technologies possible. So conceptually, you can see how that might be possible. Practically, we still face many challenges. And one of them is to actually really understand how buildings work, when during the day, what activity, and which systems need what energy. And we are working on that so that the buildings can become a better participant in a smart grid. So if you think about a building, the person that has to run the building, like Stanford, sees for every building this kind of performance. Every building will have some kind of duration during which it's designed and built, and some cost, initial cost, investment cost needed for the building. And then it will have some kind of facility maintenance cost, changing the light bulbs and things like that. It will have some building operations cost, the energy, gas, typically the utilities, and it will have some business operations cost, the salaries of the professors and so on. And it will have some duration during which it is productive. And it will create some value. So every building, if you took a snapshot of a building, you could draw this picture, and you could put amounts there. The challenge is that when you design the building, initially, we would like to have perfect visibility into the future. So when we make decisions about building materials, about layout, about energy systems, we can do those in the context of the cost and value over the life of a building. That is not yet common practice. That is not yet possible. We don't really have the data to support those decisions, and we have not yet developed all the engineering methods to do so. But that's our vision, that at any decision during the operation as well, we make decisions during the operation of the building in terms of retrofits, in terms of adjusting of the operational strategy, but especially during design and redesign of buildings. We want to understand the trade-offs that we are facing looking ahead in the future of these buildings. So if you look at the the Y2E2 building, you saw the atria as a major strategy, right? And what's the trade-off there? Okay, you get more light into the building, and it makes the building more airy. On the other hand, we're giving up square footage where we could put people and they could produce work. And so how do you trade that off? Right, we put heavy concrete floors into building so that we can use the cool air that we get for free during the night in cooling the building. And we have the thermal mass that keeps it and releases it during the day. But that heavy concrete mass required a stronger structural system because we have earthquakes here than would have otherwise been needed. So there was an extra cost there. So you face lots of these trade-offs that have implications, as you can see on these aspects. And so our vision is that we can create tools that allow building designers and builders and operators to understand this picture and make all the decisions in the context of evidence about each of these costs and values. Because today, the picture presents itself something like this. I'm not sure we can really call this engineering. Here you see about 100 buildings for which a couple people looked at the energy performance, and these are buildings that are LEED certified, so those are buildings where people actually wanted to pay attention to the energy consumption. And if the buildings actually met the energy consumption that the designers predicted, all the dots would fall on this line. So buildings on this line or close to this line perform as they were designed. So you see some buildings that are performing actually better. Those are above this line. And you see also quite a few buildings that are performing not so well. So, I mean, of course, in a way you could say, well, we should have these buildings up here. But I would even argue that we want to be accurate in our predictions because a building owner allocates money to different parts of a building. And they might have used money somewhere else if they had known that they can be up here. Or there might have been other decisions they have made if they had known they're here when they thought they would be here. So for me, that's sort of just an indication of the pitfall, of the difficulties in today's practice, that today's methods of predicting the performance over the life of a building are not as good as they need to be. So to improve that, we have really a three-pronged research approach. We do some top-down research where we characterize buildings according to their energy use. That's fairly new work. That's really only possible very recently because it's only recently that we're starting to get some detailed data about buildings, not just daily or monthly averages. We're doing some bottom-up characterization modeling of buildings, like Y2E2, the building you just visited, is one of the main case studies there. And then we're doing case studies around the country, around the world, sort of learning from the best. What are good practices we see today? What is sort of the best in today's practice? So I'll share some examples from these research areas. I'll go very quickly just to give you a glimpse of this work. And of course, if any of this is interesting to you, then please get in touch and we'll find a way to work together. Key aspects in this area are, key areas where we need to do some research are metrics, how we define energy efficiency, energy performance. What are the metrics we should use? May sound at first kind of obvious, but when you start to think about it, it gets actually, I find, quite interesting. We need to close the loop between predicted and actual performance, so that we can, and we need to characterize energy consumption. The world is quite different compared to 10 years ago. I have been on the Stanford faculty now 20 years and 14 days. So usually I don't know it that precisely, but since I started on September 1, 1991, it's easy to calculate. Now we have dramatically more awareness on these issues. We have dramatically more computing power, and we have dramatically more data. And those are all needed to do this type of work, right? And I've already mentioned the kind of things we need to improve. So, in terms of metrics, I think that's really the big deal, because if you have the wrong metrics, you're going the wrong direction. A very commonly used metrics for buildings is kilowatt hours per square foot used, or some measure of energy per square foot. So these are two, I'm giving an example of metrics using the story of metrics around an example from Disney. As most large building owners, Disney is very interested in improving its environmental footprint, very actively working on that. So they looked at their retail facilities, and you see in left in blue 2 years of data for a retail building at Hong Kong Disneyland, and you see on the right in green 2 years of data of a retail building in Orlando. So the question is, which of these building operators should get the Christmas bonus for energy performance? Well, it's pretty easy. The guy in Orlando, right? Because the building operator, I think it was a guy, he was able to operate the building with a third less energy than the Hong Kong, or the Hong Kong guy needed 50% more energy for the same building with the same function. So, So on the other hand, the Hong Kong guy has a trend that's in a better direction, right? So maybe you base in Hong Kong the bonus on that, right? So you already see, do you pay it on actual performance or on trend? What actually happened here, they told the Hong Kong guy and said, you're using way too much energy. You got to go over to Florida and see how they're using, why they're able to operate their store at with a third less energy. So the Hong Kong guy flew to Disney World. And he walks into the store and says, wow, this is weird. You guys have the doors closed. And the Florida guys looked at him and said, what do you mean the doors closed? Of course we have the doors closed. I mean, it's hot outside and we can't cool the whole park. We have to cool just our store, right? I mean, obviously air conditioning is the big energy hog, right, in both climates. So then the Hong Kong guy said, well, but if I close the doors, no, my customers will not come in. It's in Chinese culture. I have to be welcoming. I have to have the doors open, right? So he went back to Hong Kong, closed the doors, energy consumption went down, and the sales went down dramatically. He said, I'm opening the doors, right? I mean, my bonus depends more on the sales than on the energy performance, right? Eventually, they were able to retrofit the building, so they put a set of fake doors in front of the real doors, and the fake doors were always open. And so by the time, so it looked like it was open. So by the time the customers had stepped through the fake doors that were open, the actual doors opened, and then they walked in. But then then the Disney analysts had another. They thought, well, what if we look at these data on different metric? So they looked at the same two stores on a metric that measured kilowatt hours per square meter per transaction. So every time somebody buys a t-shirt or keychain or whatever, it's a transaction. And now look at this data. Why the heck do the Orlando people need 80% more energy than the Hong Kong people on that metric, right? So, I mean, I have a guess. I think in Hong Kong, people are used to tighter conditions, so I think they can put more merchandise into smaller footprint, which you probably couldn't get away with in Orlando, is my guess. But it shows a dramatic difference in performance, right? Do you want kilowatt hour per square meter? Not a bad thing to be low on that, right? Or do you want kilowatt hour per square meter per transaction? Also not a bad thing to be low on that, right? And so my point here is we should think about, in light of this picture, whether we want to focus on the cost side of the equation, which is kilowatt hour per square meter, or kilowatt hour per square meter transaction, which also brings in the value, the purpose of the building. My recommendation would be to do both, because whenever we use a single metric, we, people, are pretty good at gaming the system. So, so that's a key aspect, I think, of energy efficiency, energy performance, to think about what are really the right metrics, because that's what will then incentivize the behavior of the people. So in terms of, there's more metrics, but I'll jump over it. I'll talk about some of the methods we're using. One is using sort of parallel computing methods that are emerging here on campus. We have one of the largest parallel computing clusters in the country or world. There's a 5,000 node computer that you might have some fun with if you like. So we are using that capability to decompose a building into lots of parts so we can very rapidly analyze a building for daylighting and energy consumption, which today takes about 1 day to run a simulation on a kind of a computer an architect or engineer would have. And so that means that an architect or engineer cannot look at a lot of options before they have to pick one. And so design is a very inexact science, rather than art. So the best way to find a good solution is to look at lots of options. So here we want to take the time it takes to do an analysis for energy and daylight down to seconds or at least minutes, so we can look at lots of options and make better decisions. So that's one type of work that's going on. The other type of work that's going on is in the context of Y2E2 and also the Santa Clara County Jail. We are collecting data every minute about the performance of the building. So at the Y2E2, we have 3.5 years of data at the minute level for 2,400 sensors. So every day we get 3.5 million data points. And we're using that to compare the actual with the predicted performance, to learn where our prediction method's not good enough, and where is the operation of the building not what it could be. I think I'll leave it at that, given the time. But that's why we're doing that, I guess, is in the Y2E2 building. The very, very first prediction of energy use was a little bit off for what we actually have. Oh, now it's working. So here is what we thought originally we were going to use. And then here is what we actually used at the very beginning of the building, since I think we have improved that quite a bit. But the issue was that we made lots of wrong assumptions here, right? And so I think an issue was we never really updated those assumptions to bring them into the decision process in terms of the systems we used. So that's where we have a very interesting interplay between people, their activities, buildings, and their systems. But outcomes a overall performance which has a big impact on the planet. But it's that system we need to improve, which we're trying to do in this work. So I'll jump through this, leave it at that. We are using a range of models to try to see how accurately can the models predict the actual consumption. Most sophisticated ones being computational fluid dynamics models to track, measure, predict the natural ventilation that's happening through the atria. So work that's just really beginning. We have our fingers crossed that after a couple of years of data collection, after a couple of years of working on the relationship, we will get a massive data set from PG&E about a smart meter data set about performance of buildings in California, because a few years ago they put smart meters in, but nobody has actually yet looked at those data and made sense of them. And so we want to understand, for example, how much energy is always on, what's variable, what seems to drive the variability. Is it the hour of the day, the season, what is it? What's the picture for a certain type of building? Here, a retail building in San Jose, and here, a high school. And so you see from day to day quite different energy needs in a high school compared to and much more uniform in retail buildings. So we hope to learn a lot more what kind of energy is actually needed when and what's driving it, so that PG&E can better predict energy demand. Then they can use much more environmentally friendly resources to cover them, and that opportunities for shifting the demand can be exploited. And finally, the last example to wrap up, we studied the Adobe headquarters, which by some measure are some of the best buildings in the country. It was the first building, one of those towers in San Jose, the Adobe headquarters, was the first building in the US to reach an Energy Star score of 100, which means it's as good as it can be. So we are understanding what are they doing, what are the strategies to improve that performance over time. And they've invested quite significantly, but have also earned a lot of money back. So I guess I was a little aggressive or spent too much time in the beginning connecting to the tour with my slides. But looking at really good case studies in the industry is a good way to benchmark the best that current engineering methods can do, engineering and management methods can do, so to allow us then to see where are the major improvements needed. But in a nutshell, our vision is to be able to predict and manage the energy and overall performance of buildings far more accurately than we can do today. So thank you.